morning, all of you. In yesterday class, already we discussed about theoretical stress concentration factor and fatigue stress concentration factor, and also I explained some simple problems on stress concentration factor. Okay, in yesterday class. In this session, I am going to explain about combined study and variable stresses. Okay, combined study and variable stresses. Study loads. Okay, study loads and variable loads. Okay, combined study loads and combined variable loads. Variable loads are fluctuating loads. Okay, and also in this session, I will explain how to derive an expression for Goodman and Soderberg stress failure graphs. Okay, this graph indicates the combined study and variable stresses. This graph consists of mean stress sigma m and variable stress sigma v and yield stress sigma y, ultimate stress sigma u. Okay, here you can observe here I am taking sigma m, that is mean stress in x-axis, and sigma v variable stress in y-axis. Okay, then after you have to take ultimate and yield point stresses in x-axis. These are mean stresses. Sigma u, sigma y are the mean stresses. Okay, sigma u is the ultimate or maximum stress, and sigma y is the yield point stress. Okay, and sigma e is the endurance limit. Okay, endurance limit is only considered in variable stresses. Okay, so that's why in this topic I consider sigma e. Okay, so from origin, O is the origin, towards right you have to consider tensile stresses, and towards left you have to consider compressive stresses. Okay, the failure points from fatigue test made with different steels on combination of mean and variable stresses are plotted in figure as functions of variable stresses sigma v and mean stresses sigma m. Okay, in practice, fatigue failures are rare when the mean stress is compressive or negative. Okay, the fatigue failures are rare when the mean stress is compressive. So మన compressive forces యాక్ట్ అయినప్పుడు మనకి fatigue failures అనేవి చాలా రేర్ కండిషన్స్ అండి, చాలా రేర్ గా జరుగుతాయి. కంప్రెసివ్ లోడ్స్ వల్ల ఫెయిల్ అనేది చాలా రేర్ కండిషన్స్ అండి. టెన్సైల్ లోడ్స్ వల్ల మాత్రం చాలా హెవీగా ఉంటాయి. Therefore, the greater emphasis must be given to the combination of variable stresses and study tensile stresses. Okay, most of the failures formed due to tensile stresses, variable tensile stresses. Okay, that's why I consider tensile stress. There are several ways in which problems involving this combination of stresses may be solved, but the following are important from the subject point of view. Okay, here three methods are used to determine the combined and variable stresses. Okay, in subject point of view, in our exam point of view, we are using three methods. To determine the combined study and variable stresses. Okay, first method is a Gerber method, and second method is Goodman method, and third method is Soderberg method. In these three methods, Gerber method is not used in present days. Okay, in present days, Gerber method is not used because some failures are there. Okay, and Goodman's method and modified Goodman's method is widely used for study of variable loads. Okay, in this session, I'm going to explain about these three topics, and also I will show you how to derive an expression for Goodman and Soderberg equations. Gerber method. Gerber method for combination of stresses. That means Gerber, how to use Gerber method for study the for a combination of study and variable loads, variable stresses. The relationship between the variable stresses sigma v and mean stresses sigma m for axial and bending loading for ductile materials. For ductile materials are shown in figure. A parabolic curve here, this line, this parabolic curve drawn between the endurance limit, sigma e is the endurance limit, and sigma u is the ultimate stress or ultimate tensile strength, sigma u. Okay, was proposed by Gerber. Okay, this parabolic curve was proposed by Gerber. Okay, these dots indicates the failure points. Okay, generally the test data for ductile material fall closer to the Gerber parabola. Here you can observe these points indicates the failure points. Okay, specimen failure points. Okay, so these failure points for ductile material closer to the this parabolic curve. Okay, but because of a scatter in the test points, a straight line relationship, these two are the straight line relationship, that is Goodman line and Soderberg line, is usually preferred in designing machine parts. Okay, these two straight lines is usually preferred in design of mechanical machine components. Okay, this Gerber method is not suitable because the failure points are very closer to the parabolic curve. Okay, that's why we are not suggesting this Gerber parabolic method. Okay, according to the Gerber method, the formula is 1 by Fs equal to sigma m by sigma u whole square into Fs plus sigma v into Kf by sigma e. This is the formula for Gerber equation. Here Fs is the factor of safety. Fs is the factor of safety, and sigma m is the main stress, sigma u is the ultimate tensile stress, and Fs is the factor of safety, and sigma v is the variable stress. Kf is the fatigue stress concentration factor, where Kf is the fatigue stress concentration factor. And here sigma e is the endurance limit or endurance strength. Already we discussed in yesterday class. Okay, please refer previous class. So this equation is useful to determine the Gerber study and variable stresses. Okay. And second one is very important in our exam point of view, that is Goodman's method for determining the combined stresses. Okay, Goodman's method is very important. From same previous graph, you can observe here this parabolic graph indicates Gerber method, and this straight line, second straight line indicates Goodman's line. Okay, a straight line connecting the endurance limit, and ultimate stress sigma u. Here you can observe here a straight line connecting the entrance limit and ultimate stress follows the suggestions of Goodman failure line. Okay, this line indicates Goodman's failure stress line. Okay, Andy. This Goodman failure line is used when the design is based on ultimate stress only. Okay, this Goodman line is useful for design of components on the basis upon ultimate tensile strength, and also it may be used for ductile materials as well as brittle materials. Okay, this Goodman's method is very useful for brittle materials as well as ductile materials. Okay, the examples for brittle material are cast iron, glass. These are the brittle materials, and ductile materials are aluminum, steel, copper. Okay, these are the examples for ductile materials. Ductile materials having more elastic nature compared to ductile materials. So compared to brittle materials. Okay, brittle materials have less elastic nature. Okay. Now this is the another relation. This one is the Goodman's failure line. Okay. For derivation of Goodman's expression, we are using this graph. Okay. In this figure, line AB, here line AB is connecting entrance limit and ultimate strength is called Goodman's failure line. Okay, Goodman's failure stress line. Okay, so if a suitable factor of safety Fs, is applied to this Goodman's applied to the entrance limit and ultimate strength, a safe stress line CD may be drawn parallel to the failure line. Okay, CD is the safe stress line. Okay, CD is the safe stress line and AB is the failure stress line. So మనకి ఈ failure stress line కి లోపల ఉన్న ఈ ఏరియా మొత్తం కూడా సేఫ్ జోన్ అన్నమాట, డిజైన్ కాంపోనెంట్స్. సో ఈ ఫెయిల్యూర్ లైన్ కి పైన మీకు వచ్చే పాయింట్స్ అన్ని కూడా ఫెయిల్యూర్ అన్నమాట. సో కాంపోనెంట్స్ అనేవి ఫెయిల్ అవడానికి ఛాన్సెస్ ఉంటాయి. సో అందుకని మనం డిజైన్ చేసేటప్పుడు మనకి ఈ ఫెయిల్యూర్ స్ట్రెస్ లైన్ కి లోపల ఉండే విధంగా మనం డిజైన్ చేస్తాం. సో అందుకని సమ్ సూటబుల్ ఫ్యాక్టర్ ఆఫ్ సేఫ్టీ అనేది కన్సిడర్ చేయాలి. ఎఫ్ఎస్ ఈక్వల్ టు 1 అనుకోండి, సేమ్ ఈ ఏబి లైనే మ్యాచ్ అయ్యింది. అదే ఎఫ్ఎస్ ఈక్వల్ టు మోర్ దాన్ 1 అయితే ఈ విధంగా మనకి సేఫ్ జోన్ అనేది వస్తుంది. ఓకే, లెట్స్ కన్సిడర్ ఎ డిజైన్ పాయింట్. హియర్ P is our design point on the line CD. Okay, by using this point I am going to derive an expression for Goodman. Okay, so here I am taking a mean stress in x-axis and variable stress in y-axis. That's why this is the point P. Okay, so the length from R to P is sigma m, that is mean stress, and the height of point P from x-axis is sigma v. PQ equal to sigma v. Okay, by using these two relations I am going to derive an expression. Okay, for deriving the Goodman's equation, first of all you have to consider similar triangles from this graph. CD is the safe line. Okay, safe stress line. That's why I am considering only CD line. Okay, so here triangle OCD is the one triangle, and triangle PQD, triangle PQD is the another triangle. So from these two triangles, okay, OCD, OCD is the one triangle, and PQD is the another triangle. From these two triangles, you can observe here theta. Theta is the common angle, common corner, and common angle for these two triangles. So the angle of ODC equal to angle of QDP equal to theta. Okay, so the angle is same. That's why I am considering these two triangles as similar triangles. Okay, already we know the formula for tan theta. Tan theta equal to opposite side by adjacent side. So from the triangle OCD, from the triangle OCD, tan theta equal to opposite side OC by OD. Opposite side is OC and adjacent side is OD. So tan theta for triangle OCD equal to OC by OD. Similar way for a small triangle, tan theta equal to opposite side PQ divided by adjacent side QD. So here tan theta equal to OC by OD and tan theta equal to PQ by QD. Okay, so angle is same. That's why OC by OD equal to PQ by QD. Okay, so you have to substitute the values of OC, OD, PQ, and QD. These values are obtained from this graph. Okay, here you can observe OC. Here O and C. This one is the height of OC. This OC line is equal to entrance limit sigma E by Fs. OC equal to sigma E by Fs. And OD equal to, from here to here, OD equal to sigma U by Fs. Okay, sigma U by Fs for OD. OC equal to sigma E by Fs. Again, so OC, here you can observe OC equal to sigma E by Fs and OD equal to sigma U by Fs. Okay, you have to substitute these two values in this equation. Okay, sigma E by Fs equal to OC and sigma U by Fs equal to OD. Okay, then after you have to substitute the value of PQ. Here PQ, from here to here, the height of PQ equal to sigma V. Okay, sigma V is the variable stress. Here I am considering variable stress in y-axis. That's why the value of PQ equal to sigma V. Okay, sigma V, PQ equal to sigma V, and the value of QD. The value of QD is equal to OD minus OQ. Okay, the value of QD is obtained from the relation OD minus OQ. Okay, the value of QD equal to OD minus OQ. So already we know that the value of OD equal to sigma U by Fs, and OQ equal to RP. Okay, the length of OQ equal to length of RP. That value equal to sigma M. So you have to substitute these two values in this equation. Here you have to cancel this Fs value, factor of safety. Fs is the factor of safety. Then sigma U by sigma U equal to sigma V by OD equal to sigma U by Fs minus OQ equal to RP. That is sigma M. Okay, this is the one relation. After that, you have to cross multiply. Okay, here sigma U by Fs minus sigma M divided by sigma U equal to sigma V by sigma U, sigma V by sigma E. Okay, from this equation, you have to separate the value of 1 by Fs value. Okay, 1 by Fs and sigma U values. That's why I am taking sigma U as from numerator and denominator. I am taking same value sigma u in left side direction. Okay, that's why 1 by fs sigma u minus sigma m by sigma u, okay, into equal to sigma v by sigma e. Cancel sigma u in numerator and denominator. After that, 1 by fs minus sigma m by sigma u equal to sigma v by sigma e. Okay, and the final expression is 1 by fs equal to sigma m by sigma u plus sigma v by sigma e. Okay, this is the a Goodman's expression. Okay, this is Goodman's expression for combined stresses. Okay, this formula is very useful for determining the values. Okay, so this expression is called Goodman's equation. Okay, this is the derivation for Goodman's method. In similar way, Soderberg method also we can derive. A straight line connecting entrance limit sigma e and yield strength or yield stress sigma y as shown here. Okay, a straight line connecting entrance limit and yield stress, okay, follows the suggestion of a Soderberg line. Okay, this line is a Soderberg line. This line connects entrance limit and yield point stress. Okay, Soderberg line is used when the design is based on yield stress. So that's why we have to design the components based upon yield strength, that is yield stress. So this method is useful for ductile materials, not for brittle metals. Okay, so this method is very useful for ductile materials. Okay, now I am repeating same procedure as Goodman's method. Here I am considering a Soderberg line. Here AB is the Soderberg failure stress line. Now I am taking factor of safety. That's why here sigma E and sigma Y is the maximum stresses. Okay, sigma E and sigma Y is the maximum stresses in this Soderberg method. Okay, now I am applying FS factor of safety to this entrance limit and yield stress. Then I got the safe stress line. This CD is the safe stress line for Soderberg. Okay, in this figure, line AB connecting entrance limit and yield stress. Okay, and the CD line connects the safe entrance limit and safe yield stress. Okay, now here also I am taking mean stress in x-axis and variable stress in y-axis. Okay, now look, now you have to consider a point P at any place on CD line. Okay, here I am considering point P here. So the position of point P is at a distance of sigma V from x-axis and sigma m from y-axis. Okay, by using this graph, you have to derive an expression for Soderberg. So here also I am taking similar triangles, similar triangle OCD and PQD. Here also these two triangles are the similar triangles. Okay, here the value mainly depends upon yield stress. Okay, the main difference between Soderberg and Goodman's method is sigma y. In Goodman's method, we are considering ultimate stress, but in Soderberg method, we are considering yield stress. That is the main difference between those two methods. Okay, so from similar triangles, tan theta equal to opposite side by adjacent side. Okay. So for triangle OCD, opposite side is OC, adjacent side is OD. And for a small triangle, opposite side is PQ and adjacent side is QD. So tan theta equal to OC by OD equal to PQ by QD. Okay. So the final relation is OC by OD equal to PQ by QD. Then after you have to substitute the values of OC, OD, PQ and QD. Okay, the values, these values are obtained from this graph. Okay, OC, the value of OC equal to safe entrance limit, that is sigma E by Fs. Okay, so the value of OC equal to sigma E by Fs, and the value of OD, here OD equal to safe yield stress. So that value is sigma Y by Fs. OC equal to sigma E by Fs and OD equal to sigma Y by Fs. And the value of PQ, equal to sigma V. Okay, PQ equal to sigma V. And the value of QD, is not here. So, but the value of QD is obtained from a relation, that is OD minus OQ. OD minus OQ. So here I am substituting the values of OC and OD. Okay. So here you have to cancel the value of Fs in numerator and denominator. Then sigma E by Fs, sigma E by sigma Y equal to sigma V by OD minus OQ. The value of OD equal to sigma Y by Fs, and the value of OQ equal to sigma M. OQ equal to RP. Okay. Then after you have to cross multiply. Okay. From this equation, you have to separate the value of 1 by Fs. That's why I'm taking sigma Y in both numerator and denominator. Okay, then the value sigma Y by sigma Y equal to 1 by Fs minus sigma M by sigma Y equal to sigma V by sigma E. Cancel the value of sigma Y in numerator and denominator. Then the equation is 1 by Fs minus sigma M by sigma Y equal to sigma V by sigma E. And the final expression for Soderberg is 1 by Fs equal to sigma M by sigma Y plus sigma V by sigma E. So this is the final equation for Soderberg equation. So Soderberg equation for combined study and variable loads. Okay. So this is the expression, final expression. Okay. In our exam point of view, Soderberg method and Goodman's expression, these two expressions are very important in exam point of view. So all of you please prepare these two equations. Okay, now I am going to explain about basic difference between Goodman method and Soderberg method. Okay, here this is the final expression for Goodman's method. Okay, here we are considering ultimate tensile stress, that is sigma U. Whereas in Soderberg method, we are considering yield stress, sigma Y. Okay, this is the main difference between Goodman and Soderberg method. That is the first difference. Okay, then after if we are considering theoretical stress concentration factor and fatigue stress concentration factor, then the expression is 1 by Fs equal to sigma M by Kt by sigma U plus sigma V into Kf divided by sigma E into K load, K size, K surface, K miscellaneous. Okay, this is the expression, final expression. Okay, so here you can observe Kt is the theoretical stress concentration factor, whereas Kf is the fatigue stress concentration factor. Kf is the fatigue stress concentration factor. Sigma M is the mean stress. sigma V is the variable stress. Okay, and sigma U is the ultimate tensile stress. Sigma E is the endurance limit or endurance strength. Here K load means load factor. Load factor. K load means load factor. For axial loads, you have to consider Ka. Ka equal to 1. And for bending loads, you have to consider K load equal to 0.8 for bending loads. Okay. For shear loads, you have to consider load factor Ks equal to 0.5 or 0.8, depends upon the type of material. And K size is the size factor. Okay. And K surface is the surface finish factor. K miscellaneous. This one is the miscellaneous factor. Okay. So these all factors are mainly influence the value of fatigue stress concentration factor and theoretical stress concentration factor. Okay. In similar way, for Soderberg method, you have to consider same equation. Okay, just you have to replace the value of sigma U with the sigma Y. Okay, just this one sigma Y and sigma U is the main difference between Soderberg and Goodman's. Okay, remaining equation is same in both the conditions. Okay, just you have to replace the value of sigma U. If we are considering the torsion or torque or shear loads or shear stresses, then the Goodman's equation is 1 by Fs equal to tau m by tau u plus tau v by tau e. Here tau m means mean shear stress. Tau m means mean shear stress. Tau v means tau v means variable shear stress. Tau u is the ultimate shear stress. Tau e is the endurance limit for shear loads. Okay. And if you are considering the value of Kt and Kf values, then the equation is same as previous. Okay, just you have to replace the sign sigma. Okay. Here load factors, size factors, surface finish factors, miscellaneous factors are same. Okay. And for Soderberg method, just you have to replace the value of sigma, value of tau u. Okay, so just you have to replace this tau u in this equation. So remaining equation is same. Okay, so you can observe here the main difference is ultimate and yield stress. Ultimate stress and yield stress. This one is the main difference. Mean stress. Here sigma m is the mean stress or average stress. Next sigma v is the variable stress or fluctuating stress. Okay. Tau m is the mean shear stress. Tau v is the variable shear stress. Okay. Here I am showing the formulas for mean and variable stresses. Here, if you are considering loads, tensile loads or compressive loads, then P max is the maximum load acting on the component. P minimum is the minimum load acting on the component, and from these two values you have to find out the value of mean stress, mean load. So mean load or average load equal to P mean or P average equal to maximum plus minimum by 2. For reversed or alternating or variable loads, then variable load P variable equal to maximum minus minimum by 2. Okay, just you have to subtract here. Here you have to just add. Okay. Now, if you are considering tensile, compressive, or bending stresses, then sigma max, sigma minimum are the maximum and minimum stresses. Compression or tensile or bending stresses. Okay, so mean stress sigma m, sigma mean equal to sigma m equal to sigma max plus sigma minimum by 2. And for variable stresses, sigma variable, sigma v equal to maximum minus minimum by 2. Okay, same. If you are considering torque, or twisting loads, then maximum torque equal to T max, minimum torque equal to T minimum, and the average or mean torque TM equal to maximum plus minimum torque by 2. For variable torque, TV equal to maximum minus minimum torque divided by 2. If you are considering shear stresses, then tau max is the maximum shear load or shear stress. Tau minimum equal to minimum shear stress. Mean shear stress tau m equal to maximum plus minimum shear stress by 2. And variable stress TV equal to maximum minus minimum shear stress divided by 2. Okay. If we are considering bending stresses, then you have to calculate value of bending moment m. So m is very important for determining the bending stresses. That's why m max is the maximum bending moment, m minimum is the minimum bending moment. Okay, mean bending moment equal to maximum plus minimum by 2. Maximum plus minimum bending moment by 2 is the mean bending moment. In similar way, variable bending moment equal to mv equal to maximum minus minimum bending moment by 2. Okay, these formulas are very useful in designing machine components. In next class, I will explain some problems using Goodman and Soderberg equations. Okay. Okay, thank you.